So hello everyone, good evening. We'll start with the last lecture where we got ended our session last week. So is there any doubt in that session related numericals or any other concepts? Okay, if no doubt, there is no doubt, then what we will do, we will try to look at some of the questions from that particular session, and then after we will start with the today's content. Is it fine?
Okay, sir.
Yeah. So I think we'll start now. So what we will do is, let me share my screen first. So are you guys able to see my screen?
Yes, sir.
Okay. So hello everyone. Today we are in the second week of this Advanced Geomatic Engineering problem solving session. The course is delivered by this professor from IIT Roorkee, PK Garg, Department of Civil Engineering. And my name is Hiren Solanki. I'm a PhD scholar at IIT Gandhinagar, and I will be taking this problem solving session of this course every Monday from 7 p.m. to 9 p.m. I'm a student from the discipline of earth sciences, and my research area is in exploring the application of machine learning and deep learning for forecasting stream flow and mostly on flood forecasting. Uh, in between, if you are not able to, like if you just log out from this meeting, then you can just join the same link and rejoin the meeting. So we'll be having till 9 p.m. So first of all, we'll try to solve a couple of questions from the concept which we learned in the first week. So we'll start with this question, which is on like accuracy of map. So we have learned the concept of scale and maps also. So first of all, the question is if the plotting accuracy of map is 0.25 mm and the scale of the same map is 1 raised to, just a minute, let me admit application. Yeah. So we learned about the map and then scale also. So here in this question, it is given the accuracy of a map is 0.25 mm and the scale is also given to us. Now we have to find out if the accuracy on map is 0.25 mm, what will be the accuracy will be on ground, or what will be the minimum ground distance that can be plotted on the map. So here, first of all, we will decode the scale. So when you talk about scale, what we have is that scale is the ratio of distance on map divided by distance on ground. So here we have 1 raised to 1,000,000. So it means that 1 mm or 1 unit on map is representing 100,000 units on ground. So if we consider this as a, yeah, so people are given answers. So I think I will log in through the other account also. So I will go through the comments as well. Just give me a sec. Yeah. So here first, so we will consider that 1 mm is equal to 10 raised to 5 mm. So if we convert that into meter or kilometer, so what we'll be having is we will be representing that 1 mm on map represent the 100,000 mm on ground. So here the accuracy which is given to us is 0.25 mm. So if we want to consider that equivalent to the ground units, we have to multiply it with the scale. So here like 0.25 mm, we will consider it to ground units and then we will convert that into meter by dividing it into 1000. So our answer will come as a 25 meter. Is there any doubt in this? So I will repeat one more time that the accuracy on map is 0.25 mm. So if we know that if 1 mm is on map, then is equivalent to 100,000 on ground. So what if 0.25 mm is on map? So what will be the corresponding value on ground? So we will get the value like 0.25 into 10 raised to 3, 4, and then after we will convert our answer into meter. So we will get 25. Is there any doubt or any question? Okay, so now we will move towards the second one. So when we talk about scale, so scale of vertical aerial photograph of an unundating terrain is proportional to which variable? So can anyone wants to answer this?
Sir, inversely proportional to the focal length of camera length.
Okay.
Inversely proportional to focal length of camera lens.
Okay. So we'll look into it. So it's also directly proportional to the height of the terrain. So I mean, you just recall the equation which we learned. Scale is equal to F divided by capital H minus small h. So it is a directly proportional to the camera focal length of the camera lens divided by height of the flight minus average height of the terrain. So our like formula, I mean the which we learned in the last class, I will just write it down. Take a pencil. So the what we learned is that scale is equal to the focal length f divided by h minus h average. So here if you see that it is a directly proportional to the focal length of the camera. Okay, and then inversely, so I will see, we will go through the formula which we learned last time, so you will get an idea. So yeah, so we are having this particular figure, and what we want is like, just copy paste our question. So here is given the scale of vertical photograph of an unediting terrain. So which we have like this. So it's like we have like it's inversely proportional to the focal length of camera. So that option is wrong because like it's directly in proportion with the focal length. Now when we talk about the height of the terrain, so this capital H minus small average. So it is a terrain height. So here what we are doing is if we increasing the terrain height, then what will become, if we increase the H average, what will happen? This denominator will become high or less. Can anyone say this thing? If we increase the H average, so height of the terrain, then what will happen with the denominator? So our flying height is constant. Let's say we are flying at 2000 meter, and when we are increasing the height of the terrain, like when we are going up on the mountains, what will happen that with the denominator? It will decrease. So if we increase particular parameter HAV, then this denominator will decrease, and if this denominator will decrease, then scale of will increase. So we can say that the scale is directly proportional to the height of the terrain. Are you getting my point, or is there any doubt? I will repeat one more time here. So scale of an vertical aerial photograph of an inundating terrain. So as you've seen in the image, like we have the formula that scale is equal to focal length of camera divided by capital H, which is the flying height of an airplane or aircraft, minus average height of the terrain. So here it is a directly proportional with the focal length of camera F, and if we take the denominator, then if it is inversely proportional with the flying height of the aircraft. So what will happen if we increase the height of the airplane, like we go up in the sky, then the scale will decrease, and vice versa. So H is inversely proportional to scale. And we talk about H average. So inundating terrain. So if we increase the terrain, then the differentiation between H and terrain will become less, and as the denominator will become less, your scale will become high, and because of that scale will increase. Is there any doubt in this?
No, sir.
Okay, so now you got an idea with all the three variables, like how all the three, camera lens, height of the airplane, and the average height of the terrain, is related with the scale. Is it fine? Okay, I think. So now we'll go to the next question, which is like the theory based, so which is also we did last time as well. So isocenter of the tilted photograph is just the point on the photograph where the bisector of an angle of tilt meets the photo. So this is like completely definition based question. So now we will go to the next question. So here we are giving one particular figure is given, which is showing the scale basically. So here you have to find out the value of x, that if we find the scale of this particular figure, what will be the value of x. So first I will give you 2 minutes, just try to do it by yourself. Use the formula of scale, also known as a representative fraction, and then try to solve this question. So basically the scale is the distance on map divided by distance on ground.
Sir, 1 upon 10,000.
1 upon 10,000. Okay. So one answer is 1 upon 10,000. So our x value of x will be 10,000. Any else, like anyone else who wants to try? Are you guys getting like what to do? So first of all, we have to find a scale. So scale is a formula of scale is distance on map divided by distance on ground. So if we can consider any of the thing, so we will consider, let's say, this one. 1 centimeter is equal to 100 meter. So for that we will do 1 centimeter is equal to 100 meter. Now what we have to do is we have to make both the units in the same particular, like we have to convert both the value in same unit. So we'll convert the meter into centimeter. So to do that we'll multiply 100 meters, so it will become 10,000 centimeter. So now it will be like 1 by 10,000. So your value of x will be in 10,000. Okay. So anything, any doubt in this question? Okay. So we'll now move towards the next question. So here it is being shown that a line measures 15 centimeter on aerial photograph. So we have taken one photograph through the aircraft in which we are measuring one line which is having a dimension of 15 centimeter, while it measures 5 centimeter on map at a scale of 1:24,000. Now the photograph was taken using a camera lens of 20 centimeter focal length, and average elevation of the terrain is 240 meter above the mean sea level, and the flying height of an aircraft above the mean sea level is, for like, filling the blanks. So can anyone tell me like how we will proceed? So first of all, like what we discussed just in the previous two questions, that formula of a scale, which is a scale is equal to focal length divided by h minus capital H minus small h. This one. Okay, everyone is okay with this formula? Okay, so now what we will do is we have focal length which is 20 centimeter, then flying height capital H we have to find, average elevation we have 240, but do we have scale? So I think in the last class some of you are asking a question like how they can change this question. So this is like a tougher version of the question which we solved in the last class. So here the scale of the particular image is not given. So first of all we have to find scale, and what is the definition of scale is distance on map divided by distance on ground, or we can say distance on image divided by distance on ground, because we are taking an image through aircraft. So here in the definition of scale we have distance on image divided by distance on ground. So instead of map we will be having distance, because we are taking an image with a aircraft which will give us the image, not the map. So what we will do is the formula of scale will be distance on image divided by distance on ground. But now in question what is given to us is they have given us scale which is a scale on map. So do not take that scale as in this particular formula, because that scale is from map, but here we are calculating the for image. So scale which we have to use over here, it is a scale of distance of image divided by distance on ground. So here scale is representing image by ground, not map by ground. But in question they have given us map scale. Okay, so we will start with the scale which is 1 divided by 24 and 30, 24,000 basically. Now we are having that line measures 15 centimeter on aerial photograph. So here in this scale, we know that on image it is having 15 centimeter. Now what will be the distance? So that we have to find like in the. So what first of all we will use the scale which is given to us, which is 1 raised to 24,000, which is equivalent to 5 centimeter on map, and we have to find the corresponding value on ground. Okay, because a line measures 15 centimeter on aerial photograph, but they have never mentioned that what is the length of line on actual ground. So using the given scale and the measurement on map, which is 5 centimeter, first we will find the length of that line on ground. So scale, which is 1 raised to 24,000, is equal to 5 divided by distance on ground, which is not given to us. So we will put all the value and we will get the that line is having the actual length of 1200 meter, or 1200 meter. So now we will use that to find out the scale. So here we have 15 divided by 100 divided by 1200 is equal. So let me rub the screen. So we having 15 by 100, which is the line, like length of line on image, divided by length of line on actual ground, which will give us scale, which is equivalent to focal length f divided by h minus h average. So if you will simplify this, the answer will be 1840. So did you get the point? So any doubt, just give a thought one more time, go through it. Yeah, any questions on this?
No, sir.
Okay. So I think now we will go to our next question. So what was the catch here? You have not given scale. So first of all, you have to find scale. What is the definition of scale here in this given formula is distance on image divided by distance on ground. But we have not given the distance on ground. So for that, we have to use the information given through the map. So we have given the scale of map and how it is, like how that line is measuring on map. So using that two information, we will find the length of line on ground, and that length we will calculate to find out the S. And once we get the S, we will find out the capital H. So now we are having the next question, which is like we have to find the Manhattan and Pythagoras distance between the point A and B. So where the Euclidean distance between A and C is 4 meter, and the Euclidean distance between C and B is 4. So, and all the square like box which you are seeing here or edges which are square, not rectangle. So one, like the length of one box will be 1 meter or 1 unit. So can anyone tell the answer? Do you want to try?
Sir, 8 and 5.7.
Yes. So can you elaborate like how 8 and 5.7?
Sir, because each unit is 1 meter, so we can just reach from A to C and from there C to B. That will give us
Thank you. So we know that the like this distance is 4 and the CB is also 4. So the Manhattan distance is the linear unit. So it will be become 8. And when we talk about the Pythagoras distance, then it is a shortest distance between 2 points, which is diagonal. So here, if this is 4 and this is also 4, So the diagonal will be like this will become 4 root 2, which is 5.7. So now after that, like which of the following map scale is most suitable for urban planning? So let's say if we are doing a application is urban planning, so which map scale is relevant for that? And your options are like this.
So 1:10,000.
Okay, so one answer is 1 is to 10,000. Anyone else wants to try?
1:10,000.
Okay, so can anyone tell why 1 is to 10,000 and not others?
So
More map details.
Okay, because we are using it for urban planning, so we need cadastral boundaries. For that, higher the map resolution or more the details, it's good for the planning. So we will take which is giving the more information, which is 1 is to 10,000. So the option number 1, first option is correct one. So now we have the next question, which is like aerial photograph is to be taken from a flying height of 2 km above a flat ground with a camera having a focal length of 200 mm. And the image format which we are using is 23 centimeter by 23 centimeter. And the ground area covered it by single photograph is like if we are getting an image of 23 by 23 centimeter, then what will be the corresponding area on ground? So here we are not having linear application, we are having the application in terms of area. So I'll give you 2 minutes, just try this question by yourself and then we will try to solve it by our. So this is a similar question of finding the scale. You will be given the scale is equal to f divided by h minus small h. So anyone? So these are the options. So here we will use the same formula that scale is equal to f divided by capital H minus h average. But here, I mean, if you have seen that the what information is missing over here is h average. So average height of the terrain. So for that they have they have used the word as the flying height is 2 km above a flat ground. So ground is not inundating ground. So height like average height will be replaced by h, and you see that height from the flat ground is directly given to you, not from the mean sea level. So this flying height is 2 km above the flat ground. So when you draw this thing, let's say this is your aircraft and this is your ground, and if you are measuring this particular point over here, and then we are having datum over here, which is a mean sea level or datum. So what they are saying, like what we are h in this question for this formula is height from the mean sea level, and h average, this will be your capital H, and the height of terrain from mean sea level is h average or small h. So here what they have done is they have directly given this difference to you. So this difference which you can see here, which is capital H minus small h, is directly given to you. So we do not need both of them separately. the denominator directly is given to you, which is 2 kilometer, and the focal length is given as a 200 mm. So plug that to value and find out the scale. So what is the scale value that you are getting? So can anyone tell me the value of scale? 1 is to 10,000. Okay.
So the answer will be 5.29.
Yeah, exactly. So scale is equal to, we have height 23 centimeter on image. So 23 by 100 divided by x, and your scale will become 200 by 1000 divided by 2000. So we will get x as a 2300 meter or 2.3 kilometer. And if we want to find out the area, we will multiply 2.3 into 2.3, which will become 5.29 kilometer square. Any doubt in this? Okay, so there was small catch that they have directly given h minus h average to you. So now based on that, we just have next question, that like in this our formula of scale, if we consider a constant flying height, capital H, then the average scale of an aerial photograph depends on which of the following parameter. So what will be the answer? So this is multiple choice question, so like more than one answers can be right.
The focal length of camera and topography of ground.
So in the formula, you can see that S is equal to focal length divided by H minus H average. So if capital H is constant, then it is depending on two parameters, small f and H average. And the previous questions in the starting of this lecture, that we have seen that f is directly proportional to scale, whereas f and HAV, like topography of the ground, both are directly proportional to the scale. So then someone can ask you the question that which of the following parameter is inversely proportional to the scale, then it will be the flying height of the aircraft. Okay. So now we'll go to the next one. So now I think we have done the pretty much overview of what we learned in the last class. So we have gone through some examples on map scale and then some of the theoretical questions. So now in the second week, you will be having a more on photogrammetry, where the first lecture focused on the relief displacement. So first of all, we will see like what do you mean by relief displacement. So for that, I mean, I will show you the example. So I mean, all of you know that the Paris Olympic is going on, and when we talk about Paris, we have Eiffel Tower, so which is a like tall building kind of structure. So you can see the Eiffel Tower is like this. So if we try to capture it through my phone, like at the exactly at 90-degree, so it will be as come as a point, like one top point and 4 point which are showing the pillar. But if I tilt my phone something like this or something like this, then what will happen that it will come what you can see here right now. So you can see the tilted portion of the Eiffel Tower. So if you see from the different, so if you're like not exactly at the nadir point, then you can see the height of the tower also, because like some of the rays which are coming from the top and some of are coming from the bottom, and that distance, like which you see, the tilted distance which you are seeing radial, is known as a relief distance. So now how to use this relief distance to find out the height of any of the objects. So similarly, like this is a 3D structure, but we will take one more example. So here in IIT Gandhinagar, we are having one structure known as a Lal Minar. So if you see over here, I will show you how it looks first of all. So basically, this is one of the watchtower which we have in a campus. So it's a tall building having 11 or 12 floors and 100 feet tall. So when we see this imagery from the sky, let's say this is over here somewhere. So now we will see the different views. So this I'm using Google Earth Pro, where you can see the different time lapses of the same place. So now if I will see the imagery at different times, you can see now it's changed. So according to the location of the sun, it will change its direction. So you can like analyze the shadow and you can tell. So now you can see, but in different images, you can see the different parts of the buildings are available. And when, like here, you can see this side of view is visible to you. So when you put all those views together, you can reconstruct the 3D image of this particular Lal Minar, or you can find out the height of this Minar also. So these are some of the more like how will it look like, because we are not capturing the image exactly at Nadir. It is having little bit angles. So because of that, we are getting this kind of view and objects are long. So this is known as a like relief displacement, and using that concept, we can find out the like height of the objects. So I mean, I think you all of you have gone through that concepts in the during the lectures. So now regarding to that concepts, which of the statement is not true? So the first statement is relief displacement is the shift in a photographic position of an object caused by the elevation of the object above or below the datum. Then second is relief displacement is always in non-radial direction from the principal point. Then third one is the relief displacement can cause straight roads to appear crooked in undulating terrain. And the fourth one is the magnitude of relief displacement is affected by the flying height of the camera, assuming everything else to be the same. So anyone wants to try this question?
So second option is incorrect.
Exactly. And
Yes, sir.
yes. So why? Why? Because I mean the relief displacement is a radial distance. So it is a in radial direction. If your object is above the ground, it is towards the point. If it is below the ground, or let's say like downward, like valley kind of structure, it is a inward side, outward side. So like it's a in the radial direction basically. So that's why that option is incorrect. So it's not true regarding the relief displacement, and other threes are correct. So now this based on this concept, like we have the next question, that a square grid is laid on the flat terrain and it's photographed from an aerial camera. The flying height and camera parameters are assumed to be constant. The camera and lenses are assumed to be perfect, free from any distortion. The image of the grid obtained from the camera is shown below, which you can see like this. So I will just change one. So you are getting this kind of image. So which statement is true for this kind of image? So what will be the direction of camera and so on and so forth? So camera is looking directly downward at 90°. The given photograph is vertical photograph. The given photograph is the oblique photograph, or the scale over the given photograph is constant.
The given photograph is an oblique photograph.
Exactly. So why? Because I mean you can see that if it is vertical photograph, then every grid you see as a square grid or the rectangle grid, and scale will be same for that if it is a 90 degrees. So other three options are in a view from the, if we are looking the object exactly at 90 degree like this. But if it is having tilted, so what was the threshold of considering the whether that photograph is tilted or not, or oblique or not? So we have seen that if the this tilt is greater than some degree, then it is considered as a oblique photograph. So can anyone recall the tilt which we learned in the last lecture? So what was the limit?
Sir, 3 degree was the limit.
Exactly. So if it is more than 3 degree, then it is for that photograph is termed as a oblique photograph. So now we have the next question. So for your information, so whatever the questions which we solved till now, so all those questions were from GATE geomatics paper from the year of 2023 and 24 on the same concepts which we learned till now. So like all of these questions from the last 2 year GATE question papers. Now the next one is based on the relief displacement. So first of all, I think we will go through the the derivation part so that you will get a more idea. So here, I mean, you can see if any two objects, I'll just make it bigger. So here you can see that this is a camera lens. So this is the camera lens and these are the two objects. So when you take those photograph of those two objects, it will come like this because of their height. So that is known as a relief. So like far, as the object is far from the principal point, the relief will be high, and like if it is like having more height, then also it will become high, which is clear from the image. Now, so this is like differentiation between aerial photograph and map, so we'll not go into that. So basically your image will look like this. Any tower if you take, or a high rise building, you can see the top point and the bottom point, and the distance between those two is known as a relief. So here you can see if you are having anything which is like above the mean sea level or above the terrains, higher objects like tree, building, then they will displaced away from the principal point, while the lower objects such as valley depressions are displaced inward towards the principal point. So you can see here like principal point is like, let's say somewhere over here, so it is like displaced outward like this in this direction, whereas if you have hills or valley, it will be displaced inside. So using that you can concept like find out the height of the object. So I mean we'll go through the derivation part. So let's say you are having this tower a naught, and you are getting a relief of that particular tower as a naught. So this distance which is a relief. So over here this is our relief. So now we want to find out that D. So we will use the similarity of triangle, and that here you can see the R, which you can see is a KA, and then RO is a KA naught. And if we find out the capital R, then it will be K naught A naught, which is the distance between the principal point and the on the tower. Now the relief will be this height which we see in the photograph, which is a naught, so which is like kept small r minus r naught. So we will use the similarity of triangle, and then like basically these two triangle we will take. This triangle O, K, A naught, and then triangle O, K naught and A naught. So using those two triangles, basically this triangle and then the bigger triangle. And then we will be having that R naught divided by F is equal to capital F, which is this one, and divided by H. So we will, like if we simplify this thing, we will get that relief displacement is RH by capital H. So here you can see that capital H is the height of an flying aircraft from the terrain. So this is your terrain. So it is not from the mean sea level, it is from terrain. Then you see the small r. So small r is the radial distance of the top of the tower, so which you are getting over here. So from here, so from principal point to the radial distance, which is known as a r, and then h, small h, is the height of your tower, so which is this one. And then d is your relief displacement. So now, I mean, based on this, we will solve some questions. So in this question, it is given that the relief displacement for a tower is 2.01 mm. And the radial distance from the center of the photo to the top of the tower is 56.43 mm. If the flying height is 1220 mm above the base of the tower, so it is given the flying height is 1220 meter above the base of the tower. So h directly is given to you. Then find out the height of the tower. So I mean, we will first put the formula, so which is like capital H is equal to dh by r, or you can say r is equal to dh by small h. So we just want to find out the small h, which is the height of the tower, which is equal to the relief into capital H divided by radial distance. So I have just rearranged the formula. In the PPT it is given that d is equal to hr by capital H. So you have the relief is 2.01 mm given to you. Then after, just convert that into meter. Then the height of the aircraft from the base of the tower is given 1220 meter. And then the radial distance from the center of the photo between principal point to the top of the tower, which is given as a 56.43 mm. So it is also in mm. We will convert that into meter and we'll put everything into meter and we'll find out the height of the tower, which is 43.45 meter. So any doubt in this question? Now we'll go to the next one then. So the next question is the relief displacement for a flagpole measured 0.457 centimeter on a vertical aerial photograph taken from a flying height of 914.35 meter above ground. If the radial distance from the center of the photo to the displaced image of the flagpole tip, it means the top, measured 7.493 centimeter, compute the height of the flagpole. So this is also similar to what we did just now. So what we have given is relief displacement, which is d, is given to us. Then the flying height above the ground, which means above the flagpole ground, like base, it is given. So capital H is also given. And then the flagpole tip, the radial distance is also given 7.493. So try to do this question and find out the height of the flagpole. So I will give you 1 or 2 minutes. Just do it and give me the answer.
So 55.77 meters.
Okay. Anyone else? So you just have to use the formula which we just used, right? Like in the previous question, which
Yes,
is
sir.
small,
55.766.
yes, dH by small r. And we will be having the D, then capital H you are having, and R you are having. So I got two answer. Now we'll go and check out. So it's 55.7. So how many of you are getting this answer? Just raise your hand. So I see three of you are getting the answers. What about others? Are you having any trouble in finding it out? Four. If you are having five, okay. Okay, I guess. So now we will go to the next question. So which is a high tower appeared on an aerial photograph taken 1000 meter above mean sea level with a camera lens of 15 centimeter focal length. The radial distance of the top and bottom image of the tower from principal point of photograph are 92.6 mm and 78.3 mm respectively. So if the average elevation of the terrain is 300 meter above mean sea level, then the height of the tower will be above the ground is fill in the blank. So here also the question is the same. You have to find out the height of the tower. Okay, so we will go with the same thing, but here we have not given the direct values of relief displacement and so on and so forth. So for that, I mean, first we will draw the figure. So we'll get what the information that they have given to us. So height of tower on an aerial photograph taken at 1000 meter above mean sea level. So capital H is 1000. After that, we are having the camera lens of 15 centimeter focal length. So F is given 15 centimeter. So this is given as F. Now the radial distance of the top and bottom image. So top, which is A, and bottom is A naught. So the radial distance for A, which is KA, which is your R, which is given as a 92.6, and K A naught is given as a 78.3. So how will we find out the relief from this? So relief displacement will be equal to 92.6, which is Ka minus 78.3. So this will give us the relief displacement in mm. Okay, and then we are having the elevation of terrain. So this terrain which we are having, it is at 300 meter. So this information is also given. So now our formula, what is our formula is H is equal to relief D into, so see, DH divided by R. So we have DH divided by R. So D is given to us, that 92.6 minus 78.3, which will be 14.3 mm. The H is 1000 and the radial distance is 92.6. So find out what is the answer. So are you getting the answer? So what answer you are getting by applying this formula? Can anyone tell me the answer by plugging this values in this formula? H is equal to D capital H by R. Anyone? So anyone with the answer? Yes. How many? How much? What is the answer?
This is around 15,442.
15,000. But I don't think so, because can you consider like tower
154, 154.42.
107.
107? Okay. So there is a catch in this question. So we cannot consider this formula directly. So I mean, when this will appear for the exam, the very common mistakes which all will do is like just plugging the values in this formula. So here I mean, see the h which is given to you, that height of h is from the base of the tower, from the terrain. And in question, what is given to us is that a high tower appeared on aerial photograph taken at 1000 meter above the mean sea level. So there will be another datum, and from that this distance is given. Okay, so here like this line which you can see is our normal terrain, and the value which is given to us, which is 1000 meter, it is above mean sea level, so which is our datum. So this thing is given to us as 1000, but what we need is we need capital H, which is the like from datum to this top of the aircraft minus your terrain elevation, which is the like value between the datum and your terrain, which is given 300 meter above mean sea level. It is given that if the average elevation of terrain is 300 meter above the mean sea level. So overall H will become here 1000 minus 300.
So 108.
Yes. So we have to consider 1000 minus 300. So which will be around 700 instead of direct considering 1000. So that is a catch in this question. So you will get 108 meter. So have you got my point? I mean, what I was trying to say when what h you have to consider here, because people will like they will get confused with the capital H used in this formula of relief displacement and the capital H which we used in the scale formula. So in the formula of scale, the capital H we have used, that is from mean sea level only. But here the capital H which we are considering, that is from the base of the tower or from the terrain. So we are considering direct H minus H average values. So I mean, just be clear with your like concepts. So what will be the H? It is a height from base of the tower to the top of the aircraft, not from the datum. If they are considering from datum, you have to do this kind of corrections. Did you get my point?
Yes, sir.
Okay. So now we will move forward with next question. So now, apart from relief, there will be some question on the parallax. So parallax is like when you have any object in front of you. Let's say I will take an example of this pen. So if I keep my pen like this, and if I close my one eyes like this, and if I see this pen, and then one more time I will close my another eyes and I will see this plane like pen. So the like position of the pen or the where I have kept it, it will not like as exactly at one location. I will see some of the displacement, or there will be two different location of this pen. So when I'm viewing point two different point of view, I can see the different position of the object, which is known as a parallax. And this concepts people are using to consider like create the 3D objects, which you are also using in the like when you are going for the 3D movie. So basically, based on these principles, we have some numericals now. So when like have you seen that like I'm keeping my pen like this, and I'm closing like the line like passing through my this straight line is a zero line, and then on this right hand side I am having first quadrant, and then this left hand side I am having the second quadrant. So if I'm keeping my eyes like this left eye is closed, then I can see this pen in the first quadrant and at the like it is 10.3 centimeter away from the main axis, which is like this. Now when I like put my hand on my right eyes, then what I'm seeing is the pen is at 3.74 centimeter in the second quadrant. So from this like your center line, it is at 3.75. So I will just draw that. So let's say this is your axis. When I'm keeping my one side eyes, then I'm seeing the pen over here, which is 10.3 centimeter from in the first quadrant. And when I'm using my another eyes, I'm seeing that pen as a 3.74 centimeter in the second quadrant. So what is the parallax which is being created over here for this point? So we have this 10.3, and then the another is 3.74. So can you calculate the absolute parallax which is we can see over here?
14.04.
Exactly. So it's a summation of these two. So 10.3 minus 3.74, which will become the 14.04. So this is the how to calculate the absolute parallax, or the change in position which is happening at absolutely. I mean, when we are viewing from two different directions. Now, if we have two different points, let's say if I'm considering this pen, then I'm considering the top and bottom both the things, and I'm kept my pen like little bit like in the this direction. So consider the examples which are having measuring the height of the building from the sky from the, or height of the building from the tree from the sky. So one tree you are seeing like this, and one tree you are seeing like this, like from another eye, and then you are seeing the top and bottom of the tree. So we want to find what is the differential parallax. So difference in the parallax for this top point and this bottom point, and the difference of their difference. So that is known as a differential parallax, which is known as this 13.5 which you are seeing here. It is a absolute parallax. So if you take two different absolute parallax of top and bottom of the object, you will get the differential parallax. So here we will get 15.2 minus 13.5, so which will give you the differential parallax as 1.7 meter. So are you able to understand this concept of absolute parallax and the differential parallax? Or is there any doubt? Because the next question is based on this concept. So if not, then I will repeat this thing one more time.
So
Otherwise,
please,
we'll go. Repeat?
please repeat the differential parallax.
Okay, so differential it means, let's say I have this pen, or consider we have this box like this. So here we have top and bottom. Okay. Okay, so we are having this top surface and this bottom surface. So when I'm keeping my eyes closed and I'm seeing the top of this particular box, and then after I'm keeping my another eyes closed and I'm seeing this top of the one more time. So absolute parallax for the top point is 13.5 meter, and the absolute parallax for this bottom is 15.2 mm. Okay, is this clear till now? The absolute
Yes, sir.
parallax, which I will get the two different position while keeping my one eye closed and then the another eye closed. So like this, you will get the two different position, and you will take a difference of it, and you will get the absolute parallax, which is for top it is 13.5 and for bottom it is 15.2 mm. So differential, it means the difference between the two absolute parallax or overall for this object. So it is 1.7 mm.
Yes, sir.
Okay. So now we will go to the next thing. So like this thing I have just told you, that we are having one watchtower in our campus, which is known as a Lal Minar, which is around approximately 100 feet taller. So basically now what we will do, like as you have seen in the Google Earth photographs, that we are having the different viewpoints of this Lal Minar. Okay. So I mean at different locations, like if a different location, if you click the picture through drone, you will see the different parallax being created. So here, I mean, you can see this, you are able to see this edge in this photograph. In this, like there is very little tilt, or it's like exactly at 90-degree. You can see very minute length of, and over here also you can see this thing like this. But you can see the uh, shadow of this particular. So here the shadow is like this. Here the shadow is less. Okay, so depending on the sun's direction, you are seeing the different parallax. So like consider instead of sun, let's say you are having your aircraft there, which is flying at a height of 850 feet from the ground. And the differential parallax which you are getting for this particular object, which is, let's say if you keep your image like Lal Minar like this and like this, the differential parallax which you are getting is 0.6 inches. So now, I mean, how to calculate height using this parallax information. So there is a formula which is like like small h, which is the height of the object, is equal to that h, which is the flying height, into the dphi. Dp, it means the differential parallax, divided by p plus dp. So p is the average photo base. Photo base means the base of the photo, which you see over here. And then you just put everything into this formula and you will get the height of the Lal Minar, which comes to be 102 feet. So and the true height is 100 feet. So I mean you will get like this, you can calculate the height of the different objects, and for more like detailed part, I mean you can see the lecture PPTs. So in that, I mean if you go through the last uh, height determination from the stereo pairs and the second last the parallax in photographs, so using those two, I mean it's based on the trigonometry principles. So this formula which is given over here, so capital H into dp divided by p plus dp. So using this concept you can find out the height of the object. So here also one example is given that the parallax of top and bottom are measured for this particular Washington monument, which is originally 555 feet long. So if you are having this uh, differential parallax and then the like base of the particular image, then what will be the height? So you just apply that formula and find out the height. So now from this we can see that the when you are calculating height of an object from this formula using the parallax, then you are having the flying height, then the differential parallax, and then the average photo base. So I mean you are having two methods of calculating height. The one which we discussed in the like between of this class, which is using the relief distance, and the second one is using the parallax. So this parallax method is more like accurate than the radial methods, the radial relief displacement method basically. So like that we can find out the height of the object. Now next question is the aerial survey is conducted with a flying height of 2000 meter above mean sea level. The baseline distance between two photographs is measured as 100 meter. If the focal length of camera is 50 mm and the x parallax is measured as 0.1 centimeter, the object height between these 2 points. So there also we have one formula and we just have to plug this formula. So I mean these formulas you will find in the class, the derivation of the relationship for elevation. So now what is the relationship between the elevation and then this parallax which is being created? So which is like after doing this derivation you will be having the final formula, which is like the h, which is the height of an object, which is capital H, which is the flying height, minus this b f divided by p. So here b is the baseline distance. So if this image, I mean, so baseline distance is the like distance between the position from where you are taking the two different photographs. So here like this distance, and then f is the focal length and the p is the parallax which is being there in your photo. So once you put everything into this formula you will get 1500 meter. Just go through this once. So we are having the h is equal to capital H minus bf divided by p, where h is the height of the object, capital H is the flying height above the mean sea level, minus baseline distance between these two photographs, f is focal length and p is the parallax. Now we will solve one more question on the same concept, that a pair of overlapping vertical photographs were taken from flying height of 1230 meter above sea level with a camera having a focal length of 152.4 mm. The distance between the consecutive exposure station, which is the baseline distance, which is 350 meter. A parallax bar reading of a point A on a photograph is observed as 10.96 and the parallax bar constant for this setup is given as 80.71 mm. So the elevation of point A above sea level is found to be, so you just have to repeat the same thing. So here I mean what we have given is capital H is given 1230. Baseline distance is given as a 350. Then F is given as a 152.4 mm. And then the P, so the parallax, which is not given directly to us. So what is given to us is the parallax bar reading for point A on the photograph is observed as 10.696 mm. And then here one thing is written as parallax bar constant. So basically this constant is equal to your x parallax minus parallax bar reading at point A. So this is the formula that you have to find out the parallax bar constant. So it's like x parallax of any given point minus whatever the reading you are taking from the, like if you are putting the instrument on the map or image and then you are finding out the parallax which is given. So using that formula, first of all we will find out the missing value, which is the parallax of x, like x parallax of the point A. So we'll plug the other two variables over here in the formula and then we'll find out the x parallax, which is 91.67. And once we get that, we will put all this value there, which will give the results as a 648.313. So are you clear with this question?
Yes, sir.
Okay. So, I mean, I think we have covered the two main concepts of this week two, which is relief displacement and then this parallax. So, in parallax, that's absolute parallax, differential parallax, and then how to find out the height using the parallax. In that also, we have seen the two different methods. The first method is to find out the height using this differential parallax concepts, and then where we have given the like differential parallax and from height of the object, and we have to find out the true height. And the second concept where we have given the baseline distance between the two photographs. So we have used two different formula. The one formula is h into dp divided by p plus dp, and then second one is h is equal to h minus bf by capital P. So these two methods and the relief displacement method, all the three methods you can use like to find out the height of the object. So any doubt in the like content what we discussed today?
No, sir.
Anyone like do you have any questions? So now in the next 10 minutes, what we will do, we will try to look at what we did from the beginning. And then after, as I did like promised in the last class also, that we will see the real life application of geospatial data sets in the last half an hour or last 20-30 minutes, whatever time we have. So we have started with some of the questions from the previous week. So the first question where is like the map accuracy is given. So we have to use scale given to us and we have to find out what is the minimum distance we can find out on ground. So basically the concept of map is 1 unit on map is equal to whatever like 100,000 units on ground. So using that we will convert 0.25 mm into a meter. So corresponding unit on ground which will be 25 meter. Then we have the scale of vertical aerial photograph of an inundating terrain is proportional to which variable. So here we had formula S is equal to F divided by H minus H average. So it is proportional to focal length of the camera, inversely proportional to the flying height of the aircraft, and directly proportional to the average height of the terrain. Then we have isocenter of tilted photograph is a point on a photograph where the bisector of angle of tilt meets the photograph. So this is like based on theory. Then we have this particular scale is given to us. So we have to find out the value of x. So we know that 1 centimeter is equal to 100 meter. So we will just convert those things into same units in meter, either in meter or either in centimeter, and we will get the answer as 1 raised to 10,000. Then the line of 15 centimeter on photograph. So here, I mean, we have same formula of finding out the scale is equal to f divided by h minus h average. But the catch here is they haven't given scale directly. So we have to plug the formula of scale, which is the distance on image divided by distance on ground. So we do not have distance on ground, but they have given the scale in map and what is the length of that line on map. So using that concept of scale, so distance on map divided by distance on ground, we'll first calculate the actual length of line on ground, and then after that we will use in a given formula and we will find out the capital H. Then we are having this grid where we have to find out the Manhattan and Pythagoras distance. So it's pretty clear. So Manhattan distance is a direct in a linear fashion. So we'll end up with 8. Whereas Pythagorean is in the diagonal, so which is 4 root 2, which will be 5.7. Then which of the map scale is most suitable for urban planning? So which gives us more detail. That's why 1 is to 10,000. Then we have a real photograph. So here, I mean, the same question where with the but we have to find out the area. So here the catch is like instead of the average height h minus h average is a separate variable, they have directly given us h minus h average by stating the flying height of the 2 kilometer above the flat ground. So it will directly give h minus h average that we will use directly. So we need focal length and the divided by 2 kilometers, so which is 200 mm divided by 2 kilometer. When we simplify it, we'll get 2.3 kilometer, and to find out the area, we'll multiply 2.3 into 2.3, which will give us an answer of 5.29 kilometers square. Then we have next question on like if we are having flight height as a constant, then which of the parameter will influence the scale of the photograph? So it's a focal length of camera and topography of the ground. So 1 and 4th. Which of the following statement is not true regarding the relief displacement? So relief displacement is always non-radial direction from the principal point, because that statement is wrong, because every time the relief displacement is in radial direction only. Then we have a square. So we have given this photograph. We have to say that which of the following answer is true. So from the look also, it's like very detectable that photograph is oblique photograph, not a taken from the 90 degree. It's taken from some angle. So the threshold is more than 3 degree. Then we have the relief displacement of a tower, which is given to 2.01 mm. Then the radial distance is given and flying height of the given. So we have to use the formula of relief distance, and we have to find out the height of the object, which is h is equal to relief distance into capital H divided by r. And the catch, like the thing which we have to consider over here is h is representing the height from the base of the tower, not from the mean sea level. Capital H is the height from the base of the tower or base of the terrain. Then we have the same question, which is like same formula. And the third question, which we solved on relief distance, is the same one. But here there is a case that they have given the height of the aircraft from the base, from base of the tower, instead of they given the from mean sea level. So we have to convert the mean sea level to the base level. So we have to do 1000 minus 300, which will give us the 700, and then after we have to do the calculation. Then we have started after relief, we started with the parallax numerical. So if one object is there, if I see that object from a different viewpoint, I will see the two different positions. So first concept is absolute parallax, which is like one you see on the, if you are keeping your pen like this, then if you close your one eye and then second eye, so what is the difference between the position which you are seeing? So that is like the first difference I'm seeing in the first quadrant, and the second one is in second quadrant. So by doing the calculation, I got it 14.04. And then same way differential parallax, if you are taking the top and bottom of the pen, like this pen or any other object, like this box, then what is the differential, like parallax of top and parallax of bottom, and their difference is known as the differential parallax. Now, how to use the differential parallax to find out the height of the object? So we have taken this example of Lal Minar, and we have used this formula capital H into dp, which is differential parallax, divided by p plus dp, which we gave us the answer 102 feet, which is around the actual answer. Then we have that next question is the same thing, like we have to find out the height, but where we have given the baseline distance and between two photograph is given. So B is given, then how to find out the height of the object. So height is equal to capital H minus BF divided by P. So using this formula, I mean, you will find out the height of the object in the same way over here also. Over here the catch was they were given directly the parallax of point A in the x direction, but they have given the parallax bar constant as well as the parallax bar reading at A. So for using this formula, first we have to find out the parallax of point A in the x direction, and then after we have to put that into the formula, which will end up with the answer of 648.13 meter. So any doubt in any of the question which we discussed today? Any questions? Okay, if there is no question, I just want to ask so I mean, is we are going in the right direction? Is it okay for you if I do like this, or you want me to slow down a bit, or any comment or suggestions? Or if do you want me to cover the similar concept before doing the numerical? Anything, any suggestions from your side? So do you have any suggestions for like how we are teaching this thing, so that we can try to incorporate that in the next lecture and we try to improve it? Anyone? Yeah, you can say like you can unmute yourself and
I'm audible.
yes, you are audible.
So can you hear me, sir?
So I mean, is there any
Hello.
suggestion? Yeah.
Hello.
Yes.
Hello. I'm audible.
Yes, you are audible.
Hello. I'm audible, sir.
Yes, you are audible. Yes, you are audible. You can say. Or else you can type also if you.
Confused. Confused.
Hello.
Troubleshooting.
Okay, so I think you can write down if you have any suggestions. So we'll take that into consideration. So now what we'll do is we'll see quickly some of the websites or some of the portals of Government of India or some portals from India where we can find out the various geospatial data sets that we can use it for decision purpose. So today we will go through the BHUVAN portal. So this is the BHUVAN portal, which is an Indian web-based utility. So I mean, this is a geo platform of created by ISRO and RSC, and then it will be useful to visualize the various geospatial data, and you can take the decisions you for various variables. So here, I mean, you can see here, like in the first, like in updates, it is showing whatever the products that they are, which are available in this and recently. Then you have, sorry. BHUVAN 2D, 3D, Light, Open Data Archives related to climate and environment, and BHUNIDI. So those things you have. Here also you can see this flood inundation. So it's in this monsoon seasons, they are giving the flood inundation maps. So I mean, you can see like how flooding is happening. So it is a 23 flood which happened in the Godavari River basin. So similarly, you are having so many data sets which are available over here. So we'll look into this portal one by one. So first, like here, the application sector is there. So in which application you want to see the data sets? So agriculture, then you have water, then you have forestry applications, e-governance applications, then tourism, urban, rural. So I mean, if you click on any of the particular application, I mean, the so it will redirect you to the corresponding webs like information. So this is the information of this water resource management support from Maharashtra. So what it is given is different water bodies which are available. So here if you click on the water bodies and if you click on that particular layer, you can see the different water bodies which are available in this area. So from this particular side, you can zoom in and zoom out the map and you can see the different water bodies. So like this, when they have mapped out the different water bodies which are there in Maharashtra, and you can get the statistics of it. Apart from it, I mean, you are having like how much fraction, like if water body is there, how much water body is full. So that you can get that fraction also by clicking on any of the particular dates, and you can see. So like its latest updates is there. You can see according to the fraction, it will change. So I mean, it will take some time in loading, but you can see the fraction, how much fraction of that particular water body is still present as on now or at the selected date. So if it is like more than 90% water body is full, you can see darker colors, otherwise lighter colors. So it is still loading, so it will take some time to load all those informations. Apart from it, what you can see here that you are having the LULC. It means that land use, land classification. Then after you are having the flood information. So any flood which happened in the Maharashtra, so you can visualize that flood, that how much area it had affected. Then some of the crop monitoring. So they are having the sugarcane crop monitoring, irrigation potential, monitoring of irrigation's infrastructure, and the field data which they have collected. So I mean, this is the one of the application in the water resource management sector. But similarly, you are having in different particular sectors. Let's say Now, if we see like what kind of data which are available in this portal, so I mean for that what you can do is you can go to this BHUVAN store, click there, and you can see all the data which are available in this particular portal. So there is a first type of data which is a satellite products. And here you can see wherever it is written file size or downloads, you can download those data set and how much space it take for one particular grid. So here the tile extent is 1 degree by 1 degree, which is you will get an image covering an area of 1 degree by 1 degree, which is approximately 111 kilometer. And frequency, it means that single image only you will get. So this is like they have created this data in 2006 to 2018. This particular version, like these are the after the doing post processing of the data which they have collected through satellite, and they have released this data during this particular year. Now this hyperspectral imager, which is having this 17 bands, which is available from 2011 and 2012, and frequency also single, so it is a single scanning of entire India. Then you have the datasets from resource set, which is available from 2009 to 2019, and it is available 3 times in a year and 8 times per year after 2016 onwards. In this datasets, you can see it is at 15 minute. So if you just click on that particular datasets, you select any of the datasets. So you can select any of the data sets with vegetation fraction. So I mean you will get your data like this. So whatever the data you want to use, satellite data. So satellite data is not available in this portal. They have shifted in this Punidhi portal. So if you want to download satellite data, you can download it from this particular portal. So I mean this is the satellite products which are available from the Indian satellites. Then we have the derived products from the satellite data sets, which is the terrestrial science products, which is cropland data sets, snow related data, water body, forest fire, hydrology, soil, land degradation, so ecosystem. So I mean there are lots of variables which are present over here, and all of it is downloadable, so you can go through it and just check out. Let's say we will see this annual crop data sets. So you have to select the fraction. So let's say we want to see fallow crop, or let's say kharif crop. Then you have to select a period. Let's say we want to select 2012-13, and I will click on view. So it will generate an image of India showing the fractional area of kharif crop between 2012 and 13, and you can download this map from here. Apart from that, I mean you are having this soil data sets as well. So 3 parameters are given, and you can, if you want to read more about like this data, how they created this data sets, you can go to this technical document page and you can look into thoroughly. So in soil property, they are having texture, depth, and mean soil carbon density. If we see soil depth, so it's 0 to 0.25, how many soils are there? Then 50 to 75, how many soil is there? Where is it available? And then so like this, I mean, you can see like most of the soil is available from 100 to 150 centimeter. So like that, you can select depth, texture, or carbon density of the soil as well. So this is like soil data sets, and we have this crop data sets, satellite data sets, water body data sets. Apart from that, you have forest fire, snow, albedo, and ice, so on and so forth. After that, you are having, so those products are on ground. So if you are working on anything on ground or terrestrial, so it is a terrestrial bodies landscape. Then it is these products are available for that. So it is name is terrestrial science products. Then we have ocean science products. So if you want to work on the oceans, then these parameters are for that. So you can see the chlorophyll, which is available in ocean surface at global level or North Indian Ocean, and then the colors, then tidal map. So various parameters related to the ocean you can see over here. So first product on satellite image, second was on terrestrial product, third was on oceanic products. Then the fourth one is on atmospheric and climate science products. So this is the climate variables like CO2 present in the atmosphere, cloud cover, how much cloud fraction is there over particular area. So I mean, we'll just go and see this thing, cloud fraction. So here, I mean, you can see, we'll select any date. Let's say, so 1st January, so you can see the clouds which are there during that time. So this kind of animations will come. So we'll see the time of during monsoons. So you can see how the pattern of cloud is changing, how it is moving. So that kind of analysis, if you want to do, you want to interpret something, you can do it from there. Then after we are having the tropospheric ozone, planetary boundary layers, so all those variables related to the atmospheric and climate science. Then we have products related to the cryosphere. So in cryosphere, we have snow cover fraction, snow melt and freeze, and snow melt in Antarctica. So two products from Himalayan region and one product from Antarctica region. So if we just check it out how snow cover fraction will look like. Similarly, map will come. You have to select the imagery. So this is available in the quite recent periods, 2024 also it is available. You click on view data and you can see this legend snow cover fraction. So we will just zoom a bit. So you can see like how much snow is available at that particular area. And then after, I mean, you can just scroll through this timeline and you can check, generate the, like you can click on active swipe and you can compare the two different layers as well. So like that analysis you can do on snow cover and snow fraction. Then we have ISRO Geosphere Biosphere program products. So above ground biomass data sets is also available at 4 different stations. Then we have thematic surveys. So this is like the data on terrestrial and on ocean. They have come back, processed the data, and then they used it for the purpose of creating various thematic maps. So in that, various applications are there, such as land use land cover map of 2005, 2006, 2011, 12, 15, 16. And this map at this particular scale, 1:25, like to 50,000. So you can see now the application of scales, now at which scale they are working. Now in a MCQs, I asked you the question that which of the product, like a scale, you can use it for the urban modeling or urban cadastral, urban monitoring or urban planning. So here now the question will be changed as which of the product from this BHUVAN portal you can use for urban planning purpose. So the same thing, this land use land cover SIS DP data sets which is available for 637 districts in India, that you can use it for urban planning purpose. So now, I mean, this is similar to what we did in the MCQs. So we will try, go and check out the different products and we will compare those things. Like when we talk about the different resolution, what does that mean actually? So we are having this three product. So this first product is like 1:2005. So we have LULC at 250K, let's say, and we will take any of the year. So now you can see the map is like this, but for the clarity, what we will do is we'll just try to look over some particular area. So let's say I will see over this any of the city. Let's say we'll take Gandhinagar and Ahmedabad. So over here. So if we take this example, so at 250K resolution, 1:250,000, your image will look like this. Okay. Now what we will do, we will change our scale and make it more high resolution. So instead of 250K, we will go to 50K for the same time, 2015-16. So now you can see that now if we go to the Gandhinagar, I mean the details which we are getting is quite high. So river like also we are able to see properly compared to the previous products. And then after now we'll go to the 10K resolution. So now if we go high, so now you can see there you can able to do more zoom in because more details are present. So now you can differentiate between in like built up also which area is popularly dense area and so on and so forth. So like this also you can go like can check out the different buildings which are available, roads which are available. So all those things you can map out using this product, which is at very high resolution, and then you can incorporate the various informations, pinpoint the school location, medical locations, and then you can generate your own geospatial database which you can use for creating smart city portal, which we showed in the last class. So I mean this is the resolution like difference in the different products or different scales, how it is different. Then we are having one product which is available at 4K resolution. So we will try to see like how that will look like. So from 250K we went to 10K, then like sorry we went from 250K to 50K, 50K to 10K, and 10 to 4. So now we will go to the Gujarat. We do not have in this. So let's say we will see some city in Himachal. Let's say Kulu. So now you can see, I mean, if I zoom it a lot, so you can see like you can differentiate so many things from this particular map. Very fine maps, you can find out like individual buildings. So this will be useful in doing the damage assessment. So you are aware about the recent cloudburst event which happened in the Kulu area. So if you want to see like how many houses got washed away because of this, so those kind of applications you can do if this data is available in that particular area. So this is like how we can use the different scales and different products which are generated different scales. And one thing that you have noticed is like when we had very big scale like 1:250K, we are able to see the details of entire India. But as we have gone towards the 4K, we are not able to see the details as a whole India because we need more amount of storage to save that particular data sets. And because of that, now it is asking a third thing also, that select the particular district or particular town, because the data is not able to show it as a whole, because otherwise the system will take time to load the graphics which is associated with that particular data sets. So are you guys clear with the concept of this scale and the various geospatial data, how to relate it with the different scales and how to use it for various applications? Any doubt in this?
No, sir.
Okay. So now what we will do is we will see some of the other products also. So first thing, I mean, I forgot to tell you that if we take this, let's say, land use land cover portal. So let's say for Gujarat, so here some tools are there like statistics. So if you click on statistics, it will give you that how much urban area is there in Gujarat, how much rural area, how much tree cover, how much forest cover is present in the Gujarat state. But if you want to calculate for your particular area, so you can get the statistics state-wise as well as district-wise. In district statistic, you just have to select any district. Let's say I will select Ahmedabad. It will give me the statistics for Ahmedabad. But now let's say if you want to do it for your own area, that you have considered some particular site where you want to do some analysis, that how much urban area is present in that particular site. So what you can do is you can create your own shape like this, and then you can click on analyze. So it will give you the statistics in that particular area which you have selected. So as you can also see that majorly portion is from the croplands. So now let's say if I select this particular area of small area where water body is there, and then I will click on analyze. So now you can see the 31% portion of this given area is filled up with the water bodies, and the 54% portion is from agricultural land, cropland, and then we have fallow land, rural land, scrubland also. So like that, you can analyze the locality, like which kind of land covers which are present in your area, and then further like metadata. So metadata is the detail who created the data sets, which methods they've used. So anything related to this data sets is given under the data metadata, who created, when they created, and then what is the specification of the data, what is the scale of the data, so on and so forth. Then you have web service over here. So if you want to import these data sets into any GIS software, whether it's QGIS, ArcGIS, or any particular websites, so you can use these URLs which are given here. So these are the QGIS, UDIG, ArcGIS, and the other users. So you can use these URLs which are given here, and you can import the data into your GIS software. And then after here overlay is operation is given, so where you can like put any other layer, let's say layer of road network, layer of railway network, layer of airports, and so on and so forth. So any infrastructure layer or any other land use parameter, if you want to compare the land use of 2005 and 2015, so you can put two maps on top of each other and you can try to compare it. So this is from 2015-16. So we can, what we can do is for the Gujarat, we'll put the layer of 2005-6. So this is land degradation. We need a land use land cover. So this is the data. So like this, you can put two or three, any number of layers, and you can change the opacity and you can visualize two or three layers together. So we'll see, we'll remove this thing from here. And then, so you can see the two different water bodies and what is the area that has changed over the time in the 10 years. So those things you can see it from here. So this is known as overlay analysis. In this course, you will learn in detail about those kind of analysis. Here, just to give you the glimpse, like what are the different geospatial data sets which are available freely and how you can use that for your own purpose. So in this, we are having various data such as flood hazard, flood layer, urban sprawl, lineament. So this is related to geology, glacial lakes or water bodies, wastelands, urban use, land use. So that is at different scales and different time interval. And then how to import that data into QGIS or any other, and whether that data is downloadable or not. So here, whatever they have given under phase 2, it is downloadable. Here LULC cover it every this coarser resolution land use maps are downloadable. However, this high resolution products are not downloadable directly. You have to pay for that. So these are the various data sets. So you can look into it. Apart from that, we are having, so if you go to BHUVAN store, we'll having all the data sets and the application part for different sectors they have created that is available from this particular individual portals. So you can look into it. So which is National Hydrology Project. So it will open up any portal which is generated using these data sets. So whatever you are interested working on, so you can click on that and you can see what are the different things which are available in that. So that's it for this data sets. Now, any questions or anything that you want to ask, or you can tell me about your area where, like, if you are working on some particular area, so what we can do is we can try to cover that particular application or some geospatial data in that particular area in the next lecture. And so you can unmute yourself and you can tell me, like, if you are interested in specific application, so that we can try to cover that up in the upcoming lectures. Yes, Abhi, do you want to say anything?
No, sir, I said just saying that what you are demonstrating is really great, and this is enough for us.
Okay. So yeah, if everyone is fine, then I will try to share different things from my side, like which is covering the different fields of any like thing. But however, if you are interested in specific field, do write on chat box or on the classroom NPTEL. So we'll try to respond that. So I will take the questions which is given there in the particular chat box which is there on NPTEL site. So you can write down, mention your suggestions, comments, criticisms, questions there, and we'll try to respond to that in 1 or 2 days after that. As far as pace is concerned, I don't think so. Like if you think it is fast, then let me know. We'll try to reduce the pace.
Sir, I have some other question about
Yes.
assignments that we are now submitting in the site. When will be that will be visible the results of this assignment?
Okay, so that date is written on the top of that. So it's written as due date is 7th of August. So after that, you will get the result.
Okay, sir.
Yeah. So if you guys have not submitted the first two assignment, please submit. The last date is 7th of August. Yeah. Okay. So if there is, yeah, do you want to say anything?
Actually, Kiran sir, I have started my session very late.
Yes.
So that's why today I can't interfere you so much.
Yes.
But
So
I will catch up the balance in the sense, and maybe from next session, maybe I will be interactive with you, sir,
okay, so
actively.
what you can do is, I mean, we are also uploading the recordings of this on YouTube, and the link of the same is also given on the NPTEL site on of this course in the discussion session as well. So you can go through it, all the sessions. If you can search this Advanced Geospatial Engineering problem solving session on YouTube, you will get the recordings of both this lecture. So this lecture I will upload today or by tomorrow. So you can just go through it once, and still if you have any questions in understanding the previous concepts, and just write a mail, or we'll cover it in the next problem solving session.
Yes, sir. Sure, sir. Sure. Thank
Okay.
you.
Okay, so if there is no more questions, then we'll end up this session over here only. So thank you guys for joining. See ya. Good night.
Good night, sir.